Okay, so where did we leave last time? Let me just check. All right. Okay, so I'm just going to remind ourselves what we just did. So here we were, just in case you forgot. So the concept of convexity or concavity. So how we verify it is if you have some function, then you evaluate it at 2 points. And if all the intermediate points between these 2 points are below weighted average of the value of the function at the 2 limits of the interval we're considering, then you know that this function is concave. So concave is always defined with respect to the origin, with respect to the 0 axis. So it's somehow linked to the concept of a convex set or a concave set, but no need to way too much on that. So consider just this. If your curve looks like an inverted ball, it's concave. If it looks like a ball that's upright, then it's convex. And if it looks like a zigzag where it goes up and down, then you know it's neither convex nor concave. So that's what we have to remember. This is the strict definition. And so this leads us to our definition of yeah, okay. And so how do we interpret it? Then if the slope of f of x at some x tends to increase, then f of x is strictly convex. And if the slope tends to decrease, then it is strictly concave. So you see it here. So here the slope starts positive and then becomes increasingly towards 0 and then negative. So then you know it's a concave function. And then if you check and you find that at some point the derivative is 0, then you just have to check the sign of the second derivative. And if the sign is negative, you know you have a maximum. And if the sign is positive, then you know you have the function was looking somehow like this. And you know that the derivative here, the first derivative is 0, and the second derivative is positive, then you know what you have found the minimum, right? So this is where we were last time. Now we're just going to continue on this and go back to our example. So back in the example. So what did I have? I had f of x is equal to x minus 12x squared plus 36x plus 8. So just for fun, now do it. So find the extreme of this function f of x and tell me whether they are maxima or minima. So how would we do that? Now we don't have that many people in the room, but still we're more than enough brain power to answer this question. So let's go ahead and do that. So what's the first step I would go for? Well, what you can do is a very good trick. is you take this function, you write it in Google, and you check its shape. So now you really know, okay, well, it looks like I have a minimum here, a maximum here. So it's very visually appealing to do that. We're going to do that. But imagine that you are at the exam and you don't have Google. So what's the, well, let's start with the first step. How do we find just critical values and people at home, maybe? Do you remember how we do that? I just did. I just told you. Oh, yes, thank you. Find the first derivative equal to 0. Thank you very much. So yes, indeed, that's the first step. So let's step 1 and they are maximum just or neither. Step 1, we find the first derivative and set it to 0. Right? Because what we want is that the slope of the function equals to 0. So f prime of x equals, so I think we did that already, so I'll go quite fast. So that's always a good idea for you to do it on your own, but yeah. I've got 3x squared minus 12, then that's 2 times 12, 24, x plus 36. Then I set it equal to 0. So then values x. How would I do that? 6 or 2? Yeah, so I would use a quadratic formula is fine. So yeah, x equals no, sorry. So 24 plus so 24 squared so what do I get? I get this is 12. So the numbers are always going to turn out perfectly fine. No, I'm kidding. So I tend to, if you haven't realized yet, I try as much as possible to give you nice numbers. So that's a trick between you and me. If you're at the exam and you find 3.45628, maybe there's something wrong. Maybe I messed up too, and that's a real answer. It's always a possibility, but if I did what I intended, normally I try to give you nice numbers. So then I get, let's divide everything by 6. So I get 4 plus or minus 2. So I get two numbers, I get 2 and 6. And now our how do I check that? So this is what we are just adding. Jose Antonio, can you help us again? Because we're having a hard time here. Second derivative, yes, good. So we check the second derivative of step 2. We check the second derivative of f of x at these 2 points. And then we know whether there are a maximum or a minimum. So let's compute the second derivative. So this is the first derivative. So second derivative. So I let you do it if you like. This is not the case. So somebody tell me what's going to be the second derivative of f of x. Yeah, perfect. 6x. Yeah, so there's nothing special about the fact that it's a second derivative. We just take the first derivative of some other function, which happens to be a first derivative. And then, so let's evaluate it at 2. I get second derivative of 2 minus 24. So that's equal to 12 minus 24, so minus 12. So 2 is a maximum or minimum. Max. Oh, good. Good, good, good. Oh, now we have many people that are awarded. Good. So is a maximum. And normally, since this is since this is a second order function, then you should look like something like this. So if I have 2 critical points, so yeah, I could have something like a inflection point, but if I have two critical values where the first derivative equals to 0, then it should either look like this or look like this. So if I find one point which is a maximum, then I could essentially be sure that the second one is a minimum. But let us be sure, because we never know. It could be an inflection point or something. So let's just write it. So at x equals 6. So we do what we have. We have that second derivative is 6 times 6 minus 24. So that's 36 minus 24, which is equal to 12. So we have what? Yes, min. Six is a minimum. Why? Because I know that the first derivative at 6 equals 0, and its second derivative is positive. So it means that the function there looks like this. And here at 6, I have the first derivative, which is 0. And the second derivative is positive because my slope is increasing, increasing, increasing. So I know that this function has to be a minimum. And let us just cut it very quickly. So this is my function. This is the trick. You use internet, and it's very nice with you. It gives you everything. And let us even be a bit more thorough there. Okay, so here I have, what did I say? X equals 2 and x equals 6. There. And 6 and more x. And then I know, first of all, that the first derivative at 2 is 0 and at 6 is 0. And I know that the second derivative is equal to, what was it, 2 minus 12, I think. I'm not mistaken. Yes. Which is smaller than 0. And at 6, I have 12, which is greater than 0. All right, so I know that this is a maximum, that this is a minimum. So this is how you find it. So for a single valued function, that's quite nice, I think. So don't worry, you get to practice with some examples. But if you learn your derivative rules, and if I'm nice and I give you only the sort of thing that we always use, so something like a polynomial expression, then that should turn out okay. Questions about this? So you take the first derivative, you find the zeros, and then you look at these points, these zeros, what is the value of the second derivative, and you know whether you have a maximum or a minimum, or an inflection point. Okay, so perfect. By the way, in the assignment, I'm asking you to do something. So where are we? Oh, yeah, so I have a quiz that I'm going to give you to do. Here I might, yeah, let's go for an economic example. So, yeah, economic example. You may remember from your microeconomics class that the firm revenue is maximized when the price elasticity is equal to 1. And so maybe, I don't know in which group you were, but in my class, I tried to explain a bit how it worked. But yeah, it was not necessary to explain it, but here we go. So if you look at it now, it's going to be super simple. So the firm revenue is maximized when the price is. Oh, sorry. Yeah, I was sharing the other screen. Here. Thank you for. Okay, a firm's revenue is maximized when the price elasticity is equal to, and it's -1, of course, because the it's because the derivative, so the demand is always a negative function, or most of the time. So then we want a price elasticity of demand that's equal to -1. So let's find out how. So the firm revenue is this. So R1, which is equal to price times quantity. Remember that? R1 the revenue. Yeah, I shouldn't say a firm's revenue, I should say a monopoly's revenue. Because that's really a firm that faces a downward sloping demand curve, so that's the monopoly. All right, here's the revenue, P of Y is the market price, which depends on so let's do that. So maximize income. Yeah. So how do you find the maximum revenue? Maybe it's too easy now that we've been talking for a while about it. Step one is, yes, step one, find the first order derivative and set it. Now I have a product. So you may remember that the rule for a product is that it's going to have two terms. So it's the derivative of the first term times the second, plus the derivative of the second times the first. So we are y equals to So I'm going to have to. So first one is the derivative of price with respect to y times y. Plus the second one is the derivative of y with respect to y. And it's of course equal to 1. So I can just write it this way. And I set that equal to 0. So in the micro class, you may remember something like delta P, delta Y. So that was just a sneaky way of using derivatives all the time, but not telling you about them. Because yeah, our lives are so hard if we can't use derivatives in economics because we use them all the time. So that we use the things like first differences and stuff like that. But at the end of the day, it's just always looking at changes of stuff with respect to other stuff. And as you're going to see, if we have this, it's much, much easier. Okay, so this is the first derivative. So what do I find? I find that so this is equal to minus the price. But now, if you remember, the elasticity is income elasticity. Sorry, price elasticity of is dy over y. Let me write it correctly. Divided by dp over. And what I can do is just multiply by p and divide by y, so I get the following. So it's like dy over dp times p over y. Right, so I've just multiplied by p and divide and y and y, and then I get this expression. And so I have a problem because here I have dp dy, and here I have dy dp. So I'm stuck. So can I do something about that? You can just venture a guess. So this is something that we've seen a few classes before, but maybe we've seen it in passing, so you don't remember exactly. So it's the inverse function rule. So, function rule. So what I can do essentially is the following. Since so what I can express is 1 over d over dy equals dy over dp. As long as dp is at 0, and of course ui is not 0. All right, so both derivatives exist. If both derivatives exist, then one over the first derivative can be the second the other derivative, right? So you see, again, all I'm doing here is moving around these things, but they're just some number that I can move around. They're nothing special, no magic with them. They're just very small, but it works for any sort of number as long as they're not zero. So very small doesn't mean they're zero. So I can just move around like this. And so here, what I can just express is the following. So here, instead of dp dy, I can just replace this by 1 over. And then this is just, but I can, yeah, you don't have to, I'm just going to show it as it's just a number. But of course, that's the elasticity is evaluated somewhere, but yeah, I don't want to carry the terms everywhere. So let's just so here, what do I get? I get then this is divided. And then let's set the -1 on this side. And this is, of course, yes. Right? So that's a very straightforward way of showing it. So you just maximize, and you remember that, so this derivative can be the reciprocal of this derivative, and you're good. Or yeah, maybe I should have written something different. What I cared about was, yeah, 1 over dy. So that's the same thing, just I just, because that's what I'm going to substitute. All right. So thing is, if so, nobody asks for a question, so I sort of can ask you some questions, but it's I'm introducing stuff. So yeah, it's I realized that actually I'm going to finish a bit early, so we're going to do exercises in class, I guess, to practice you as much as possible for the exam. Yes, so but I finished earlier than last year because last time people asked more questions. Yeah, okay, another application. I'm going to let you think about it. Okay, try to figure it out for yourselves, and then we can check it together. All right. So then you can think first. Okay. So another application from microeconomics. So oh yeah, there is one thing that I haven't done here. Yeah. Okay. Something I haven't done that I should have done. So little detail. So it may sound strange to say that it's important. It's a little detail too, because we know it's true, but let's just verify to be sure. So it's good form. It's a good thing to do to make sure that when you want to find a maximum, then you confirm that you did find a maximum. So how would I confirm that I found a maximum? because now we found the value of the marginal revenue when it's equal to 0. But now what we want is to make sure that we indeed found a maximum. So how will I do that? It's always take the second derivative. Yes, thank you, Mr. Santa Maria. So yeah. So we take the second derivative. So we know that the first derivative of the revenue is this. So all of these little details I went very quickly last time because I was running out of time, but since we have time, let's do them. So we verify. Second derivative. Revenue. So this is the first derivative. So it's e squared, oops, over dy. And what do I get? Well, it's d squared p over dy squared times y plus, yeah. And then this is dy dy. So this is 1 again. And here I get dp of y dy. So then what is it? It's so this should be positive or negative? Yes, it should be negative for a maximum. If I'm looking for a maximum, then I want a second derivative that's negative. What do I know about this? Is this positive or is this negative? So this is a demand function. So how does price change when the quantity sold increases? What? Yes, decrease, exactly. Yeah. So dpy is negative because the inverse demand py has a negative slope. But what about this thing there? So this is annoying. Yeah, it's not annoying, but is generating. So not important. But you know it's there. So it's the second derivative of the income. Let's not go there and ask what shape could it have, whatever. If it's a linear function, so if the inverse domain is linear, then this is equal to what? So let me give you an example. So if I have something like Px, Py equals 10 minus y, for instance. So the sort of demands that we would be using in some microeconomics model. So what is the first derivative? So Py equals 2. So just to probe, are you comfortable with this, or do you have questions? Or I really don't want to go too fast if you're lost. So really tell me if I've done that 10,000 times. So for me, it's like could do it in my dreams. So of course I'm trying to know where you're at, so I don't go too fast. So yeah, but if you have a difficult time, just tell me. So yes, this is equal to -1. I just take the derivative of this, and this is 0, so -1. And so what is the second derivative? So square. So this is equal to 0. Thank you. So yes, so you see that if it's linear, then the second derivative is equal to 0. So that's why we don't care too much about it. But in principle, it's there. We have to make sure that we indeed found a maximum. Right? I don't know if there's some way to know something about this, but I'm really not sure. But in principle, it's okay. So some other application of microeconomics. So it's going to look like this. Maybe it's a bit easier. So let's go ahead and find this. So we know that let's call this section applications. Or economic examples. Then, so the marginal cost crosses the average cost at its minimum. So this is also a thing that we've seen a lot in microeconomics. So let us verify this. So let's verify this. Cost function C of y. So now verify this, please. Try to think about it for a few minutes, and then I'll see what happens. So try to remember what is the marginal cost, what is the average cost, average cost, and how would you verify this this thing to be true? Yes, Steve, perfect. So that's a starting point. So we know that the average cost is AC equals CRY. So let's find out how do we find the minimum of this. So you can see if you have ideas of what we should do, or if you're unsure, then just ask. So I'm just going to remind you what cost curves look like. Oh yeah, dc dy. So yeah, dc y dy, what is this? Yes, that's a marginal cost. And the yes, awesome. So now last thing we have to do. Maybe microeconomic is far back. When did you take your 201 class? Yeah, so in which semester are you? You're in the fourth semester? Wow. Okay. So last time I assumed everybody knew perfectly well all their microeconomic stuff, and I asked some in the exam. And let's just say it wasn't all that great. So okay, I understand now why you're having a bit more troubles. So these are all microeconomic notions that you may remember or not. But yes, the marginal cost crosses the average cost at its minimum. So let's go ahead and verify this. So now let's find the minimum of the average cost. Okay, so I'm going to be, this is very useful so that you can, but so did you, it's just, did you take 2-1? Did you take some other microeconomics class after that? No. All right. Okay. So I'm thinking I'm giving you, making you a favor by using a microeconomics example, but now I'm saying maybe that's not so true, but still it's a good exercise. Okay. So how would I find the minimum of the average cost? Step one, always the same. Yes. Let's so take the derivative of the average cost and set it to 0. Yes. So DAC of y dy. And then I can let you do it if you remember a bit. So you have a quotient. So do you remember exactly what you get for a quotient? Not really. So a quotient is a bit like a product, but it's a bit different. So the quotient is if I have like so quotient rule. So if I have so if I want to take the f of x, g of x, so if I have something that the two are functions of x, but they are a quotient, then I get so this is something you really have to learn by heart. It's going to help you all your life, even when you're retired at 70, you're always going to use this. I don't know, but it's f prime of x, g of x, minus g prime of x, f of x, divided by g of x squared. So this is the quotient rule. All the time, if you want to take a derivative of two things that are, so two things are a function of the same variable, then, and they're one divides the other, so it's always this. We checked that like three classes ago, I think. So then this I'm going to get dc of x of y dy times y minus dy is 1 times c of y, and then divided by y squared, right? So yes, so again, f prime of x is dc of y dy times g of x, this is just y, minus g prime of x, it's dy dy, so it's 1, times f of x, it's just c of y, then divided by whatever I had at the denominator, but squared, so y squared. Okay. And then I set that to 0. What do I get? So this gives me so so let's multiply by what. So anyways, this is yeah, I have a 0 there, so I can multiply by y on both sides and do that. So what do I get? I get 0 here, and I just get one fewer y's there. Then I'm just going to split these two things. So all right, so y divided by y, this disappears. This is so what is dc of y dy? So we just saw it, so please remember. Yes, dc of y. And what is c of y divided by y? Yes, ac of y. So this is what we wanted to show. We wanted to show that the marginal cost crosses the average cost at its minimum. So we found that if we are at if we found some y value, yeah, some y value such that the derivative of the average cost with respect to y equals to 0, then this is going to be true. So yeah, so maybe I can refresh your memories by showing you a picture. So what that looked like, something like this. So I had and then the average cost was something that looked like very large initially. Oops. Average cost. And then the marginal cost would be something like spread. Then does that ring a bell a bit or not? Yeah. So yes, then this is it. And if you want the intuition for this, so why is the average cost decreasing when the marginal cost is below it and then increasing when it's above it? So think of, say you have a class of students and I have some class average that's, let's be optimistic, 80%. And then I continue adding students to the group. But now, so I'm here, I'm at 80%, but now I'm adding to the average bad students that have, say, a grade of 60%. So how is my average going to change? Well, of course, now I start at 80%, but I add to the class people with 60% average, 60% score. So then the average goes down and down and down and down. Always, if I add some bad student to the group, then the average goes down and down. But then at some point, I start adding good students again. So the average starts to go up again. So imagine I'm at 70, but now I add students that got 71, 72, 73. So then the class average is going to start to increase again. So this is why every time you add a marginal cost that is below average, then the average goes down. And then when you add costs that are over the average, then again, the average starts to increase. Oh, sorry for people at home. I didn't. Anyways, I'm going to copy this. It's hard to multitask with so many different mediums. But, okay, so now I know why microeconomics example are not so easy for me. Because yeah, I just saw that like 3 or 4 weeks ago. So I'm like, yeah, of course they know that, but yeah, well, for you it's very far away. Okay, so what could I do? Well, I can check whether I have a. Yeah, so I could check whether my fund minimum, because that's what I was looking for. I was looking at the minimum of the average cost. So I want to be sure that this is the case. So again, let's take a second derivative. So squared equals to is that what did I do here? Yeah, no, I want to set this to 0. Yeah, so this is what I. So this is the first derivative. So let's look at the second derivative. So b squared is squared. And then again, I get, oh yeah, I get a mess again. So I have how many terms now? Many. 1, 2, 3. What do we do with this? So, and again, it's going to be a matter of marginal cost. Yeah, okay, make sure that we're talking. Yeah, okay, let's do it for. So I won't ask you to do something super long at the exam. So, but let's see what I would do if I had a super big expression like this. So first of all, let's cut it in sections. It's always better to divide and conquer. We know that if it's if it's a sum, then you can take the derivative of a sum is the sum of the derivatives. So let's go ahead and derive this. So here I have, yeah, here that's a product, and here that's a quotient. Or actually, it's a two quotients. So then I would have e squared dy times y minus d squared dy divided by y squared. And here I have this y times y squared minus 2y. 2y is dy squared dy, so it's 2y times c of y. And this is, meter and square root. I get this very fun expression. So can I do something with that? So I have to make sure that this is positive. So I think for you, it's going to be useful just to be able to try and do it for yourselves again. It's always the same. It's rules of taking derivatives. So it's good practice, and then you can make sure you get the same thing as I did. So let's set everything under the same same number. So y to the fourth. So here I would multiply by square, 2 square minus this plus this. Yeah, it really is a mess, right? Nothing simplifies. Oh yeah, this simplifies. This is -2. Yeah, okay. This is the same. But other than that, I can't really tell. So what one of the y's can simplify. I didn't plan on doing something as messy as this. So can I say something about this? So I have a 2 there. Oh yeah, I know what I can say. Have 2. So that's 2 times this expression there. And I'm going to make it even easier for you. So 2y, and then this y disappears, and then this y. So can we somehow make something, some magic happen with this? What? What is wrong? Yeah. So yeah, I think what I did is okay, yeah, so what I had is -2. Yeah. So less, and then here what I did is multiply and divided by y. And then I put the and yeah, there's minus. Okay, thank you. You're right. I forgot this thing. That's what I want. Yeah, thank you. Okay, so my question is, can we do something about this thing? Does that ring a bell to you? What is this? dc of y dy? People at home, dc of y dy, what was that? What was it? Marginal cost, yes, marginal cost of y. And what is this? Average cost. And what did we just say that these two were equal to? Or rather, what did we say that marginal cost was equal to? It's equal to average cost. We just said that what we're looking for is a point where marginal cost equals average cost. So then this can be equal to 0. So remember. So then this goes away. So that's equal to, then this goes away too. And then what do I know? So what is this? It's no. This is the second derivative of the cost with respect to y. So it's also equal to the change in marginal cost with respect to y. Because the marginal cost is the derivative. So this second derivative is the first derivative. And do we know its sign? No? Are you sure? If you look at my picture here, what's the derivative of the marginal cost with respect to y? The derivative is the slope of the curve. And I'm at this point here. So is it positively or negatively sloped? Yes, it's positively sloped. So I know that at this point it must be positively sloped. So it tells me that I am, so I know that. And this is so larger than 0. So, this is equal to 1 over y times, which is, of course, larger than 0 since 1 over y is just some positive quantity. And so do I have a maximum or a minimum? If the second derivative is positive? Yes, since the second derivative is positive. Let's not essentialize myself, so we know we have right? And this makes sense because if the marginal cost crossed the average cost, not from below, but from above, then what would that mean? Well, it would mean that the average cost was increasing, and then it's crossed, and then it starts to decrease. So the average cost would have indeed have been maximized at this point. But here it's, I know it's a minimum because I have decided that the first values of the first units of production are small initially, and then cost more and more as time goes on, right? So yeah, this was 2 applications of maximization to economics. So yeah, we're out of time. So yeah, let's. I'm going to give you other exercises to do for the session. But anyways, you had a ton of exercises for the TA session last time. So I can tell you what there is to do in the end. Yeah, so really there is a Taylor theorem. I think I'm going to do it maybe next week. We'll see. Next week we see another application of maximization with when we have 2 variables, but where one can be substituted. So it's, I know I shouldn't do maximization with 2 variables, but now it's sort of cheating because I can substitute one and eliminate it. So we're going to see that next class. All right, so thanks everybody.